Okay, here is just a great problem that I'm going to hopefully be able to illustrate this for you, an approach to card problems. So we're going to talk about a full house in poker, which I'm sure most of you are aware of what that means, but it consists of three cards of one rank and two cards of another rank, for and ranks being aces, twos, threes, fours. And it's just a five card hand. So our hand is full of jacks and nines if we have three jacks and two nines, for example. So we're trying to find how many full houses could be represented from a standard deck, and then we'll talk about what's the probability of actually being dealt a full house in just five cards. So I like to think of this as what I'm going to refer to as the 52 card salad bar. Where I have a salad bar laid out here and I have aces and twos and threes and fours, fives, sixes, sevens, eights, nines, tens, jack, queens, and kings just laid out there for me. So all of my aces are here, twos, etc. As I go down my salad bar, I don't have to pick everything. I can pick only the things that I want. And so I'm going to talk about choices. So you can imagine me up here carrying my plate and just walking down the salad bar looking to fill my full house. And as I'm going down, I look at the aces, I look at the twos, the threes. No, but then I get to the fours. And in the fours, there's a club, and there's a spade, and there's a heart, and there's a diamond. I look at the fours and I say, hey, the fours are pretty good. That was a choice I made. I haven't selected which of those fours I want yet. I just selected I want fours. Well, how many choices did I have for my first selection? I'm not choosing clubs, spades, hearts, diamonds. I'm choosing ranks. I had 13 choices. And then once I selected those fours, now I see within the fours, I get to choose three of those. So this is going to be selecting a small group from a big group is either a combination or a permutation. So now we have to understand a little bit about poker. When the cards are dealt to us, we can take the cards and shuffle them around within our hands. In other words, if I am dealt, or if I choose clubs, spades, and hearts, four of clubs, four of spades, four of hearts, that is exactly the same as had I chosen four of hearts, four of spades, four of clubs. The order I chose those in made no difference. So this is a combination. So to review, I walked in, I chose a rank out of the 13. From within that rank, I chose three cards. And now I continue looking throughout the salad bar. I could go back and look at aces and twos. I could come back this way, or I could continue down there, but I now have 12 choices. I have to choose another rank, and I'm going to suggest I chose the tens. And once again, in the tens, I have clubs, spades, hearts, or diamonds to select from. I only need two this time. I'm still selecting from four, and the order still doesn't matter. So times combination from four, I'm choosing two. And I'm going to claim that's the number of full houses that we could have. In this case, that turns out to be 3,744 different full house salads that we could create. Seems like a pretty big number. And that is actually the conclusion of problem 65, but there's a very similar problem to this in our next section, probability. So I'm going to use this video in that section as well and just conclude, and we're going to ask what is the probability that just dealt randomly five cards we actually receive a full house. Well, the number of ways we can receive a full house is 3744 we've discovered. That's the number of full houses. But the number of possible hands, the beauty of moving into probability is the denominator in probability is just the number possible. That is almost always the easier number to find. The numerator usually takes a little bit more work. In this case, our salad bar analogy. Our denominator, though, we don't get to just look at the cards. We're just dealt 5 out of 52. And once those 5 come into our hand out of the 52, it doesn't matter what order they came in. Therefore, we have this. 3,744, that's a lot of full houses. Maybe it's pretty likely. Not when we realize that C52.5, there would probably be a lottery out there pretty close to this where you have 52 numbers, you have to choose 5 correct numbers. This is 2,598,960, or approximately, I should say, 0.00144, which means if we were sitting down playing poker and just getting dealt 5 cards, we could expect to get just about 3 full houses every 2,000 hands were dealt. Again, that's just 5 cards. I'm not replacing any of those. I'm not choosing my best 5 out of 7. So as we can see, not a really likely proposition.